Hey, greetings, everybody. Today's lab is about what you see up here. It's called line spectrum. So for the past couple of days, we've been talking about where electrons can live around the nucleus. And there's this model called the Bohr model, right, that proposed that you have your nucleus in the center and that you've got these energy levels surrounding the nucleus. Right? And they believe there to be 7 of them. And electrons can possess the ability to jump into heightened states, which we now know are called excited states. Right? But they don't stay in those excited states. Inevitably, they fall back down to a lower energy state known as the ground state. And when they do that, they release energy. That energy, they believe, can come off as a wave that has a certain frequency, because we know frequency and energy are linked. In the flame lab the other day, we let all of the electrons fall all at once, and all of those waves merge together for us to see one unified color, whether it be blue or purple or pink or red. Right? Those waves all merged. Right? But in reality, there were many, many different transitions. 3 to 2, a different electron goes 3 to 1. That releases a different amount of energy, a different package of energy, which is known as a photon. Right? So we were getting many waves given off during the flame lab, but we couldn't tell the difference between them. The idea behind a line Spectra Lab is that we use a device, right, called a spectroscope that can separate that light into its characteristic wavelengths. Right? The device isn't anything crazy. It looks like this. Right? You look into the one end, and you hold the other end up to some sample of excited electrons. Today's is going to be a tube filled with gas. Right? And depending on the identity of that gas, its electrons will fall from excited states to ground states, and it will release a package of energy, but then we can use this thing to separate it into its individual components. Right? Now, because you aren't with us, you can't go through the process of looking through this and seeing that. But luckily for us, what I can do is give you what you would have seen through the spectroscope, and then teach you how to interpret it, which is the main idea behind the lab, understanding these electronic transitions and how a spectroscope works, and getting the link between the graphical data that I'll show you and what you see on the line spectrum. All right, so I'll show you how everything sets up, though. All right, and here's one of the tubes. Right, and inside this tube, you can see, if I can get it close enough, that we have neon. Right now, the neon isn't doing anything because its electrons aren't being excited. But if I take the neon and I put it into this power supply, when I turn this power supply on, it should excite the electrons. Now I'm going to turn the lights out so you can see it. And if I come back here and turn on the power supply, you can see that that is emitting light, right? And in this, it looks like it's simply emitting orange light. But in reality, if I look at this through a spectroscope, you're going to see it's emitting much, much, much more. So if I were to show you what the neon looks like through a spectroscope, you're going to see that it's not quite as simple as you may think. All right, so what I'm going to do with you is open up what the neon is going to look like. Now, what you're seeing right here is what the spectroscope would show you. And if I toggle down to what the neons look like, these are all of them. If I show you what a neon spectrum looks like, oops, sorry, back here. There's my neon. Okay, you're going to see that it has a lot of different waves that are leaving. Each one of these lines that you see represents an energy transition. Right? Maybe the sixth level to the fifth, maybe the sixth level to the fourth, maybe the third to the first, right? But every time we get a different electronic transition, you see a different package of energy, a different photon release. That translates to a line that we would be able to harness in our spectroscope. So all of these things merge together to produce that orange light you saw coming off the bulb. And the spectroscope will rip it apart into its individual pieces. So what we can do is record where we're seeing these individual lines, and this is called a line spectrum. And we can know about how many different electronic transitions that there are. Some line spectra can be pretty complex, like this guy. Other ones can be simpler. This guy here only has 5 lines. Some are even simpler. This guy here only has 3. So the idea behind it is each element has its own line spectrum, which can be useful because line spectra, if it's unique to the element, can be used to identify an unknown, right? I can trap a sample of a gas and excite its electrons, and if its spectroscope picture looks like what you see right here, I know whatever element matches that picture must be my unknown sample. And this is how they can figure out what elements live in the sun. Even though we've never been there to gather a sample, we can harness the light that's released and look for these signatures. All right, so there's another type of graphical analysis that I'm going to show you. And if I do that, you're going to see that there's a link between each of these graphs and the line spectra that you would have harnessed. All right, so give me a second to find it. Sorry, wrong page. All right, here's my emission. All right, so if I were to look at something like hydrogen, right, now I were to show you, right, its emission spectrum, which is what we really see. You're going to see, all right, a colorless graph, all right, that gets harnessed. And if you're looking at this graph, how it reads, that each one of these big peaks that you see represents what you should be observing as a line in your line spectrum. All right, so one of the things we can do is I can show you a side-by-side of this. At least I can try to. Okay, and if I do that, what you'll see, if I look at this graph right here, I'm seeing a pretty big peak at, maybe it'll let me drag this to the left. Maybe not. Alas. All right, I'm seeing a big peak here, right, at a wavelength of not 700, not 600, not 650, but just above 650. If I bring up this substance here, do I see a line right above 650? I do. So that makes me think maybe this could be hydrogen. You have to go through and check them all. So now I'm seeing a cluster of peaks right here near 600. That makes me think I would see a bunch of yellowish orange lines right near 600, right? 1, 2, 3, 4 of them. And if I look at my picture, not sure those are there. So I'm starting to wonder maybe this isn't hydrogen. If we look here, I should see a very big characteristic peak down here, just below 500, right? And the higher the peak, the brighter the line is in your spectroscope. So I should see a blue line that is showing up somewhere in the 490 region. So I come here, substance cannot be hydrogen because I am missing that big peak at 490. I have another big peak down here in the purple range and another one in the purple. And this unknown that I'm showing you here doesn't have those, so that I can't say that that is the hydrogen spectrum. So we would move on to the next one. Right? You kind of play this game as you keep looking at your spectra. Then you go back. So I know I'm looking for something that's got not a lot of action, the 450 wavelength, right? There's no peaks there. I should see a big blue peak, 490 or 480. I should see another purple peak, right? That's somewhere near 430 and another purple peak down near 410. And I need that big reddish orange line right up by 650. And so you work your way through your unknown. I start looking, okay, I have the red, looks like I have a couple of the oranges. Okay, you could sell me that this peak here might be this cluster of peaks. But when we get to the 550, there's nothing at 550. In my spectrum, if I look at what my spectroscope showed me two green lines at 550. This can't be hydrogen either. So I go to the next one, right, and I look. I should have a big red peak right around 650. Looks like we have it. Should have some action right near 600 that's yellowish, couple different peaks there. Okay, that could be those. And we keep scanning down. Really shouldn't see much of anything in between 5 and 550. Look at the spectra, 500, 550. I'm not seeing anything, so that's good. Should see a big old blue peak just under 500. Here's a big blue peak under 500. I should see two purple peaks down in the 410 and 430 range. And here's just over 4. That's right about 430. That makes me believe that this unknown from my packet must be hydrogen. Right, so that's what we're doing back in the lab. What we do is we go back to the lab, we look through our spectroscopes, we get this picture. Then what I do is I have you guys record what those wavelengths are. Right down here, where am I seeing lines at? That's going to let me match it up to these emission spectra. And then I can use a packet of my known emission spectra to link it to my unknowns. And I'm going to share both of those things with you guys on the Google Classroom. All right, they'll be in here. Align Spectra Lab. And if you go into here, you'll see here are my unknowns, the unknown PowerPoint. Here's the lab format. All right. Here, oh, I'm sorry, the lab procedure. Here's the lab format. And the last two things that you're going to see now that I'm done recording this video, or I'm going to upload the Spectra packet, which is this guy. The one that we were looking at that had all of the peaks. All right, so I'll upload that whole packet and the name of the elements at the top, just in case you're curious. And I will upload the video itself to go with your Spectra unknowns, which you will have. All right, so one of the bigger questions in the lab is trying to figure out who are the 12 unknown substances. You guys will fill in your data tables based off of these pictures. So for this one, I'd go to unknown number 12. I would say I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 lines, and I would record what I think each of their wavelengths are in my data table. All right, and if I show that to you, right, you would be down in here, right? Line number is simply the first line I see, the second line I see, the third, the fourth, the fifth, all the way down. So you would number 1 through 16. Some spectrum might fill the table. Some spectra may only have 3 lines. It depends on how complex it is. Right? The color is simply, what is the color of the line? Red, orange, orange, green, 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 maybe light green, light green, light green, dark green, dark green, dark green. And then their wavelength is the number where you think it's hitting on the axis. That's what you'll do to fill out these tables. So your tables might not match perfect with mine. You may have some small tables and big tables. Right? And because we'll make this a formal lab where you can write it up and type it, you can just manipulate your tables how you would like. And then you've got your post-lab questions down here, which is part of the lab report. Right? And that is the main goal of the lab, right, for what we're doing. All right, so hopefully this helps you out with identifying what we're working with line spectra. All right, I'm always available for questions. All right, so please do not hesitate to call. Hope you guys are having a good day.